before we talk about specific antenna properties, it's really important for all of us to remind ourselves the most basic antenna element, which is this isotropic radiator. So an isotropic radiator, given here schematically as this red dot, is basically an imaginary antenna that will radiate equally well in all directions. So it will isotropically spread its energy, its radiated energy, and so if you're standing on any part of this sphere, you will basically feel exactly the same power density. It has absolutely no preference in terms of direction, and if you feed it with some type of input power, let's say 1 watt, it will take this power and it will spread it to so many watts per meter square on the surface of a sphere. Now, isotropic radiators do not exist, so don't try to build one. It's actually impossible. Don't try to buy one, but it's a very important imaginary element, because when we will compare the radiation properties of normal antennas that you can actually buy, we will actually compare them to an isotropic radiator. For example, when we define gain of an antenna, we will define gain compared to an isotropic radiator. As you can see here, the power density that you feel is actually a function of distance. It's a function of the radius of that sphere. One property that we will find very useful as we do this discussion is this property called radiation intensity, which essentially tells us how power is being spread out without making it a function of distance. So we will basically take the power density that you will see here, which is the power over 4 pi r square, and multiply that with the range square. So essentially we make radiation intensity a range-independent quantity. So in other words, the mathematical definition of a radiation intensity is simply radiation density, watts per square meter times square meter.